Hi everyone, am I audible? You can just write in yes if you can hear me. Okay, great. So we can start then. So today we are going to start a new topic, and the name of the new topic is graphs. So what according to you is a graph? Can you define it for me? What is a graph? Edges and nodes, okay? Okay. The second guy also talks about nodes and relationship between those nodes, okay? Cool. So pretty much you guys are right. So when we talk about graph, we say graph is, a collection of two things. V means vertices. You can also call it nodes. And E means edges. But wait, we have already seen a data structure, which is a collection of nodes and edges. Haven't we? Yes or no? And what was that data structure? It was a tree. So tree also is a collection of vertices and edges. So how come graph is different? Yes. So few of you are already answering. In tree, cycles were not allowed, but in graph, cycles are perfectly allowed. In a graphs, there might or might not be cycle. Okay, cool. So let's take example of a very simple graph for you. So let's say you have got a node which is A, another node which is B, and there is an edge connecting them. So you can say that, hey, this thing is a graph which contains two vertices A and B and one edge, which is this. Okay, before we move into the technical jargons of graph, the technical terms, tell me, is there day-to-day utility of graph? Do you see some software applications installed on your mobile phones that make use of graph data structures? Yeah, maps is probably the best example. So all of you must have used Google Maps to navigate your way from one place to another place, right? So what Google Map does is all the different places are stored as nodes and the roads connecting them are stored as edges. That is what it does, as simple as that. Okay. There are many other examples also. So for example, in Facebook, the way people are connected is shown in form of a graph. So for Facebook, my Facebook account is a node, and all the people who are my direct friends are directly connected to me via edges. Now, there might be some people, now some of my friends may have or will have some other friends also who again may or may not be directly connected to me. So that all thing is a graph, and that is useful for a lot of purposes. One thing that should come to your mind is, how many of you know about this feature of mutual friends on Facebook? Do you understand what's a mutual friend? Okay. Do you believe graph representation would be useful to compute mutual friends? Who are the mutual friends of, let's say, two people? It would somehow help us or not? The answer is yes. So let's say there is a person one, okay, and person one is directly connected to person 2, 3, and 4. And let's say there is another person called as A, and A has a friend of Q, A has a friend of R, A also has these two persons as friend. So now if somebody asks you for the mutual friends of P1 and A, so who will be the mutual friends of P1 and A? Can you answer that? P2 and P3, right? So others who are not responding, I can assume that you don't know mutual friends. So for that, you need to know mutual friends. Okay. Anyways, it's a very trivial thing if you guys have been using Facebook. So we'll move ahead. Cool. So now let's talk about these edges. Okay, so there are two categories of edges. The first category is unidirectional, and second category is bidirectional. Okay, the meaning of bidirectional is that if there is an edge from A to B, there is also an edge from B to A. Or think of it in this manner. Every edge is like a relationship. So if there is a relationship from A to B, there is also a relationship from B to A, right? That is called as bidirectional. But unidirectional means that, hey, if there is a relationship from A to B, it is not necessary that the relationship from B to A will also be there. So tell me, when you look at friends graph on a Facebook, is it having bidirectional edges or unidirectional edges? It has bidirectional edges. Why? Because if you are saying that P1 is a friend of P2, then you should also say that P2 is a friend of P1. No one can stop you from that. Okay, can you give me example of some social media where the edges are unidirectional? Twitter, okay, Twitter, Instagram, yeah, those are pretty good examples. So on Instagram, you must have seen that if a person P follows person Q, then it does not mean that Q also follows P, right? So for instance, if you, for example, follow a Hollywood superstar, it does not mean that Hollywood superstar also follows you. So based on the requirements and needs, certain times graphs have bidirectional edges and certain times they have unidirectional edges. Okay. Is it clear to everyone that what is the meaning of bi and unidirectional edge? Yes or no? Okay. There is one more categorization. So this was one categorization. Another categorization is that your edges, they could be weighted and sometimes they could be unweighted. Okay, what is the meaning of weighted? Weighted means that edges, they have some number associated with them, and that number can denote something. For example, let's say there are 4 cities and they are A, B, C, and D. And there are several roads that are connecting them, for example. Now these roads will have some length, or let's call it distance. So let's say this distance from A to C is 5. This distance is 2, this is 4, this is 9. So in this case, I would say this graph is a bidirectional and at the same time, it is weighted also. Is it making sense to everyone? What is weighted? Yes or no? But look at Facebook graph, Facebook friends graph. Is it weighted or unweighted? Does it make any sense to keep it weighted? The answer is no, because it just establishes a friends relationship. So you cannot say that P1 and P2 have 90% of friendship, but P1 and P3 have only 20% of friendship. That Facebook doesn't do. If it starts doing, then that's a different sort of thing. Okay, makes sense to everyone? Okay, cool. Now, I also talked about trees before talking about graph. So if you have a tree, for example, let's say this is your tree, and I pick any random pair of nodes, let's say this and that. I ask you a question that, hey, how many paths are there connecting these two nodes? What will be your answer? Yeah, so in case of a tree, there will be exactly one path. And I had explained it very in a very detailed manner that why it will be so, because in tree there are no cycles, and because there are no cycles, there has to be only one path. Because the moment you are able to see that there are two paths connecting a particular pair of nodes, it means that there must have been a cycle. So here that path, for instance, is this. But in a graph, in case of a graph, there can be multiple paths. So let's say you have got some nodes like that. and let's say these are the edges. Okay, so let's say you have to go from A to B. Let's say this is C and D. Can you see that there are multiple paths that connect A and B? And can somebody count how many paths are there? Could be a challenging problem for you, but think of it. How many distinct paths are there? Okay, no need to count for now, but let me tell you, this is one path, this is another path, this is another path, this is another path. There are a lot of paths, okay, that connect A and B. Okay, now let me ask you one more simple question over here. Let's say there is a graph in which the number of nodes is n. In which the number of nodes is n. Then what will be the number of edges? How many edges would it contain? If I had asked you this question for a tree, then what would have been your answer? Tree with n nodes, how many edges would it contain? N minus 1. We have already learned that. But how about a graph? Okay, so in graph, it looks like, hey, we are not sure. Okay, so let me ask you, if there are n nodes in a graph, what is the maximum number of edges that it can have? This is an easy question now. Some of you are saying n factorial. N factorial, if you're saying n factorial, what is the number of nodes here? 4. And what is 4 factorial? I think 24. Can you add any new edge in this thing? In the current graph, tell me. Can you add any new edge in the current graph? The answer is no. In the current graph, you think you cannot add any new edge. What kind of new? See, every edge that you create, it connects two nodes X and Y. So you tell me any two nodes. You tell me AB, there is already an edge. You tell me CD, there is already an edge. You tell me BD, there is already an edge. So what is the number of edges that you see over here? The number of edges over here is 6. 1, 2, 3, 4, 5, and 6. So of course, 4 factorial will not be answered. Those of you who are saying 2 raised to power 4, that will also not be answered. N minus 1 will also not be an answer. So how to think about it? How to think about it? So guys, we can just say that, hey, at max, what can happen is that every pair of nodes is connected. Every pair of nodes is connected. Now, if there are n nodes, how many pairs are possible? How many distinct pairs are possible? So using basic maths, that is NC2. Those of you who would have given some time to math section on the Renaissance dashboard, you should be able to very well appreciate this thing. And what is NC2? NC2 is n into n minus 1 by 2. So this is the maximum number of edges that you can have. And when I'm talking about edges, I'm naturally not talking about self loops. Some of you might be thinking about, hey, what about this edge? I would say, hey, let's not talk about things like that for now. We are talking about simple graphs. So the maximum number of edges that you can have is n into n minus 1 by 2. Is it making sense to everyone? Yes or no? Okay. Now, such kind of graphs, for example, in which the number of edges is maximum, which is n into n minus 1 by 2, are also called as clique. Now, no need to remember it. I'm just telling it for curiosity. So such kind of graphs are clique, in which the number of edges is at its maximum value. Okay, now also tell me, if there are n nodes, what can be the minimum number of edges? Minimum number of edges in a graph having n nodes. Okay, Ahmad is saying n minus 1. So Ahmad is basically assuming that in the bare minimal case, our graph can just be a tree where n minus 1 edges will be there. Others, what do you think? 0 is the right answer. Why? So let us say we have got 3 nodes, and those 3 nodes are A, B, and C. This thing, is it not a graph? The answer is yes, it is a graph. It is a graph that has got 3 nodes and 0 edges. Nobody told you that you have to have edges. At certain times you can have 0 edges, and that is perfectly okay. So it means that number of edges in a graph with n nodes will be something in between 0 to this number. Is it making sense to all? Yes or no? Okay. However, an important thing that I wish to tell you over here is such kind of graph is a disconnected graph. Disconnected graph. And it is very important to understand what is a disconnected graph. But before that, we should understand, hey, what is a connected graph? So let me tell you what is a connected graph. Connected graph is that in which no matter what pair of nodes you choose, there is at least one path. Okay, there is at least one path between each pair of nodes. This is what your connected graph is. So tell me, is this a connected graph? Yes or no? It certainly is a connected graph. You tell me which pair of nodes is not connected, or which pair of node does not have a path. You tell me. No matter what pair you take, this, there is a path. This, that, there is a path. There is always a path. Are you able to understand when I say connected, what I really mean? Okay. And when you talk about this graph, then here I can say, hey, there is no path between A and B, or there is no path between A and C. Okay, let's change this graph. Let's add some more components to it. Okay. Okay, this entire thing is a graph which has 1, 2, 3, 4, 5, 6, 7. There are 7 nodes and there are 3 edges. Okay. So what do you think? Is this connected or disconnected? This is disconnected because if you take A and D, then there is no path that connects A to D, right? I cannot reach from A to D. Okay. However, if I ask you a question that, hey, how many connected components it has? Then you should ask me, hey, what is the meaning of connected component? And this is one of the most important concept in graph. Connected component of a graph is that subgraph or a smaller graph which is connected in itself. So if I say this is a connected component, because if you just consider this much subgraph of the bigger graph, all the 2 nodes are, any pair of nodes are reachable from one another. Same is the case here, same is the case here, same is the case here. So I can say that in this big thing, there are 4 connected components. Is that making sense to everyone? Yes or no? Okay, now let me ask you one basic question. When you look at Facebook graph, what do you think? The entire Facebook graph, will it be connected or will it be disconnected? Or what do you think? It can very well be disconnected. You don't need to think about entire Facebook. You can just think about maybe all the people that you have seen in your life throughout. You might not be friends with all of them. It can very well happen that person A is friends with B, is friends with C. And so this can be one graph, right? And then another graph can be like that. Person P is friends with Q, Q is friends with R, right? So Facebook graph can actually be disconnected. In fact, in reality, it is disconnected, right? Does it make sense to everyone? Are you able to think why would it be connected or disconnected? Yes or no? Okay. Cool. So guys, so far, all the examples that I have been showing you in those examples, the edges have been bidirectional. Okay, so bidirectional, it means A connected to B, also means B connected to A. Okay, let me ask you, if you have got a graph where the edges are unidirectional. Unidirectional means it says that, hey, you can go from A to B, but you cannot come back from B to A. Okay, is this graph connected? Yes or no? Okay, let me ask you one simple question. Can I go from B to A? Then how can you say it is connected? Is it connected? Yes, no? The answer is no, it's not connected. So keep this thing very clear in your mind. If you have been given directed edges or unidirectional edges, you have to be super careful about that. Okay, great. Let's move. Now we will talk about graph representation. What are the ways to represent a graph? So we know how to represent a tree. We also know how to represent a linked list maybe, but how to represent a graph. So let's say you have been given a very simple graph that looks like A connected to B connected to C. How can I represent it? Have you guys already learned about some representations? If yes, please feel free to talk about those. Very first representation that we have is called as adjacency matrix representation. And what is adjacency matrix representation? It is a matrix basically. And if there are n nodes, then the dimension of the matrix will be n cross n. So here there are 3 nodes. So the dimension of the matrix will be 3 cross 3. Okay. And now let's say you have A, B, C here, and you have A, B, C here. Now, whenever you talk about a particular cell, then this cell corresponds to BC, right? So if there is a direct edge from B to C, let me tell you, I'm not saying path, I'm saying direct edge. If there is a direct edge from B to C, this value will be 1, otherwise this value will be 0. So tell me, is there a direct edge from B to C over here in this graph? The answer is yes. And that being the reason, here you will have 1. Okay, tell me what will be the value which will come over here? It will be 0. Why will it be 0? Because this cell corresponds to A to C. Now from A to C, there is no direct edge. So it will be 0. So if you fill everything, this is what you will get. Okay, so this is what your adjacency matrix is, and it is an n cross n matrix. So it very well represents a graph. Why? Because the dimension itself will tell you how many nodes are there, and the members of the matrix will tell you that what kind of edges are there. I mean, which nodes do they actually connect. Now, there are some properties of this matrix. The very first property is that this is symmetric about this line, about this diagonal. So you can see that whatever you have below it is a mirror image of what you have above it. Okay, and this is very natural. Why this is very natural? Because adjacency matrix of I comma j, let's say if it is 1. If it is 1, that means from I to j, there is a direct edge. Moreover, if that direct edge is bidirectional, then it is guaranteed that adjacency of j comma I will also be 1. Does it make sense to everyone? Yes or no? Right? Similarly, if this was 0, this also has to be 0. So you can see that whatever is the value at, what is this cell? This cell is 0, 1. So 0, 1, whatever is the value here, the same is the value here. What is this? This is 0, 2. So whatever is at 0, 2, that is present at 2, 0 also. So this is an important property about it. Okay. Okay. Will symmetry still be there if the graph has directed edges, which is unidirectional? The answer is no. And you guys should be able to figure that out. Why? Okay, let's talk some quick things about it. What is the space complexity associated with this representation? N square. Why? Because you need to build a matrix whose dimension is n cross n. Okay, there is one more representation, and that is, we'll talk about whether this representation is cool or that is cooler, but that is called as adjacency list representation. What is adjacency list representation? Adjacency list representation says, let's say there is a new graph where the nodes are 0, 1, 2, 3. Okay. It says that, hey, what you should do is you should create a list for every node. So for example, you have a node called 0, there should be a list for that. Similarly, for 1, there should be another list, and so on and on. And that list should contain the directly attached neighbors. For example, for 0, the directly attached neighbor is only 1. For 1, the directly attached neighbors are 0, 2, as well as 3. Okay, what will be the adjacency list for 2? Which elements will be contained in it for 2? Yeah, it will be 1 and 3, because when you take a look at 2, it is directly connected to 1 and 3 only, so they will be there. Similarly, for 3, 3 is directly connected to 1 and 2, so they will be there. So this is another representation that you have. Now, how can I store this representation? So this was quite easy. All of us know a two-dimensional matrix or a vector of vector or a list of list. But how will you represent adjacency list representation? Yeah, you can again use an array of array or a vector of vector. But the point to keep in mind over here is that the different vectors will have different sizes. Like here for 0, the list is of size 1. For 1, the list is of size 3. So you can prefer to have a vector of vector. Why? Because vectors are dynamic. Okay. So because they are dynamic, so you can make sure that the first list has a random size and the second list has a different random size. So you can have an adjacency list like that. Now let me ask you certain questions. What is the space complexity associated with this representation? For previous, it was n squared. What is it over here? Think and say, take your time. Worst case n squared, but don't tell me worst case. Can you tell me general case? Okay, so let me tell you one thing, all of you. This is a very important point. All the graph algorithms that we will learn about, we will talk about their complexities in terms of V and E, where V is number of vertices and E is number of edges. So let's say you have a graph with V vertices and E edges. Now you think and say, what will be the space complexity associated with their adjacency list representation? Okay, can I say it will simply be equal to the sum of sizes of the list? Yes or no? So find the size of the list, sum them up, and that will be your answer. Now, let me ask you one simple question. If there is an edge between 1 to 2, listen it very carefully. It means that 2 will appear in the adjacency list of 1. And it also means that 1 will appear in the adjacency list of 2. What does it mean? It means that if there is an edge that leads to 2 elements. So if I and j are connected, then j will be there in the adjacency list of I. And similarly, I will be there in the adjacency list of j. So if there are 1, 2, 3, 4, if there are 4 edges, and because each edge is accounting for 2 elements, then these 4 edges will account for 4 into 2, which is 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. Is it making sense? How many of you get that? Right? So the sum of sizes of all these lists will be 2 into E, where E is the number of edges. Moreover, there are v vectors also. There are v separate lists also. So there are pointers which are pointing to those vectors. So it will be v plus 2 into e. So order of v plus 2 into e. 2 can be ignored. So you can say it will be order of v plus e. Is it making sense to all that how it is order v plus e over here? Yes or no? Yeah. Okay. Why v? It's very simple to say. You have several lists. This is list 1, this is list 2, this is list 3, this is list 4. How do you know that these lists even exist? You know them because there are pointers pointing to those. Like you have list of 0 pointing to this, list of 1 pointing to that. So should you not take into account those pointers contribution as well, as many pointers as you have? Does it make sense? Where from did that v come? It should naturally make sense. Okay, cool. Okay, now tell me, so which representation do you think is better? Here it was order v square in terms of space, and here it is order v plus c. So what is better? So most of you are saying that second representation is better. And the reality is, yes, second representation is better because it saves a lot of space. Why it saves a lot of space? Because what can be minimum value of E? Tell me the minimum value of E. The minimum value of E is 0. Number of edges could be 0. And the maximum value is V squared. So only if you have a dense graph means there are a lot of edges, then only the space complexity of adjacency list would be order V squared. Otherwise, it will definitely be smaller than that. But in adjacency matrix, every time, even if you have a graph that has 0 edges, then also you will have order V square space requirement. Does it make sense to everyone? Yes or no? So what we'll be doing is we will always be sticking ourselves with this representation, adjacency list representation. Okay, having said that, let me tell you one more thing. It is not wise to say that, hey, in every respect, this representation is better than that. It is not wise to say. How? Let me ask you a simple question. Let's say there are so many queries and a query is of form I, j. Okay. And you have to tell me whether there is a direct edge between I and j or not. In that case, which representation will be better? The first one or second? The first representation will be better because you can directly check what is the value of matrix Ij. But in this case, you will have to literally iterate on the ith list to figure that out. Is it making sense? Yes or no? Right? So you have to basically take a call. Okay, cool. So let's move on. Now we will come to the important graph algorithms. The first and the most frequently asked, like in 95% of the interviews, when they ask graph questions, it is around graph traversals only. And the first graph traversal is DFS traversal. Okay, do you guys recall the traversals of trees that we had learned? You guys recall pre-order traversal? It was recursive in nature, right? Okay, great. So let's say you have been given a graph that looks like 0 connected to 1, 2, 3, and then 4, 5, and 6. Okay, in tree you had a concept of root. In graph, do you have a concept of root? Yes or no? No, there is no concept of root. Can I do one thing? Maybe I can pick any random node as a root randomly according to my will and start a pre-order traversal from there. Start a pre-order traversal and then assume that it will definitely touch upon all the nodes. Yes or no? Okay, so I'm going to just write a pseudocode of the thought that you might be getting. So let's say you want to start your traversal from a random node. This is your function. And what you will do is you will first print the node. And then you will call traverse for all its neighbors. This is all. This is all that I have. Is this a correct algorithm to implement? Will there be any issues with it? What kind of issues will be there? The biggest issue will happen when there are cycles. See, in trees, the situation was that there was no cycle. So when you used to come from root to below the root, there was no way you could go back. There was no way you could go back because all these edges were directed. If there was a pointer from here to here, you then did not have a pointer way back from here to here. Similarly, if you come back from here to here, there is no way to go back. But in case of graph, it can very well happen. For example, if you start your traversal from here, so you print this according to this statement, and then you make a call to this. And then you print this, and then you make a call to this. And then you print this, and then you see this is connected, you make a call to this. Then again, this makes a call to that. You'll be trapped in cycles inside a graph. And this can very well happen. Is it making sense to all? Yes or no? Yeah. So how to prevent these cycles? In order to prevent these cycles, what we'll do is we will keep track of what nodes are visited. Okay. So you need to have something called as is visited. And this can be a Boolean structure. So let's say we have a Boolean array whose size is n, where n is the number of nodes. And initially it is all false, false, false. Everything is false because initially the things are not visited. And now the algorithm that I have is quite simple. What it does is it prints the node. And after printing the node, it marks the node as visited. So this is another important thing that I'm doing. If I'm printing a node, I'm saying that, hey, this node has been visited. And now I am calling traverse for all the neighbors which are still unvisited. So this is one minor change that I'll bring in my pre-order traversal and my job will be done. What is that minor change? Keep track of which nodes are visited and which nodes are not visited, which can be done using a simple Boolean array. Does that make sense to everyone here? Yes or no? Yeah. Okay, great. So looks like this idea can be easily implemented. So let's take a look at the code. So let's say I have a method called as DFS. This DFS, whatever we have learned right now, is a depth first search technique. So it is nothing special. It is just pre-order with a Boolean flag to keep track of things. Okay, so let's say we have this function that takes in a node, and you can start DFS from any node. It is up to you where you want to start with. So let's say you have this simple graph with you. You can start from 0, you can start from 1, you can start from 2, it is up to you. It is guaranteed that all the nodes will be traversed, only their order could be different. Okay. So this is what we have. Okay. The first thing we will do is we will print I, which is the current node. Okay. And after that, what we'll do is, let's say we have an adjacency list representation, which is a vector of vector. This is our adjacency list. So what we are going to do is, after printing I, we are going to take a look at the list of I and what nodes are there in the list of I. Now, for those nodes which are still not visited, I'll make DFS call again. So I'm going to say for all j that are present in adjacency list of I. Okay. The first thing that I'll do is I'll check if not of is visited j. So let's say you have a list of I that contains elements. So if there is an element j over here, that means j is directly connected to I. So you'll first check whether j is already visited or not. If it is not already visited, then there are two things that you are going to do. First thing is you are going to say that, hey, I'm going to convert its visited flag to true so that nobody calls it again. And after that, I'll invoke DFS function on it, DFS of j. Yeah, this is the code that I'll have. Does it make sense to everyone? Yes or no? Yeah. Okay. I'm just writing the pseudocode over here because I want you guys to give a good try to implement this in your own language. How to create adjacency list, I have talked about it extensively. We have talked about it extensively in your Renaissance dashboard. You can even check that out over there. Okay, now here what we are doing is, before we are calling DFS on J, we are first making is visited of J as true. So there are both the patterns. Certain times what people do is people make the call and after printing, they mark it as visited. And certain times people first mark it as visited and then call DFS. It is up to you how you want to make those calls. There is no issue with that, but you have to be consistent. When I say consistent, there will be a main function. And that main function will start DFS from certain nodes. So let's say you plan to start from here, you will call DFS 0, but you have to be consistent. Because before you call DFS 0, it is your responsibility to mark is visited of 0 as true, so that it doesn't get visited again. Okay, does this make sense to everyone? Yes or no? Right? Okay. Okay, we will talk a little more about this algorithm, but before that, can somebody tell me its time complexity? Again, your answer should be in terms of V and E. Or let me ask, have you heard of its time complexity from your friend, from some book? You know, a lot of people in interviews I have seen, they mug up the time complexity of DFS, that it is equals to certain thing. By the way, it is equals to V plus C. But when asked to explain, hey, why it is order V plus C, they might have no answers because it takes an effort to understand why is it order V plus C. Okay. But before that, let me ask you one thing. Do you believe that the complexity, the time complexity of this thing will depend upon what representation are you using? Are you using list representation or are you using a matrix representation? It will depend on this. Do you believe so? Yes or no? The answer is yes, it will definitely depend upon that. And let us understand how. Okay, let's take a look here. DFS function, how many times will it be called? If there are V vertices, how many times will it be called? This is a simple question. It will be called for V times. If there are V nodes, it will be called for V times because you never repeat something. You mark it as visited and you never repeat a call. Now, if let's say you are at a particular node, which is this. Now you need to figure out that which all nodes are directly connected to it, so that now you can make your calls for them. If you have an adjacency matrix representation, then what you will have to do is, if this is your current node is ith node, then you will have to go to row number I, scan this entire row to figure out at what places you have one, and then make call for that. So it means that this task for every node will take you V more time. Why V more time? Because the size of this row is V units. Is it making sense? Yes or no? Right? So it very easily looks like you will be calling this DFS function for V times. And every time you call it, you will be scanning through this row to figure out how many ones are there and at what indices those ones are there, so that you can make the call. Okay, so it means it will be V into V, which is V square. So the complexity will be V square if you are using adjacency matrix representation. How is it clear to everyone? Yes or no? But if you use list representation, then the life will be a little different. And how it will be different, let us understand that. Okay, now I'm asking you some very basic question. Forget about everything else. Tell me, if I run this algorithm on top of a graph which has V vertices and E edges, can you tell me how many this statement will be printed? How many times this statement will execute? V times, right? Because you do not print a node again and again, you print it only once. So this statement will execute only once, right? Okay, how many times this much of code will execute over the lifetime of this function? So let's say you triggered DFS 0, now it triggers so many things on and on and on. So over the lifetime, how many times this particular code will be executed? Think of that. Okay, so let's imagine you had your first list which just had one element in it, second list which had 3 elements, next list which had 2 elements, next list which had maybe 4 elements. Now keep looking very carefully. So let's say the first DFS call that was made for the node whose list is this. It means this thing would have worked for 3 times. And then the next DFS call that you made was for this. So this thing would have worked for 4 times. And then the next DFS call was for this 1 time. And then for this 2 times. So can I say that over the lifetime of DFS recursion that happens, this piece of logic will run for as many times as the sum of sizes of the lists? Can I say that? Yes or no? Easy to understand? So I can say that, hey, what is time complexity of a code? Time complexity of a code is that how many times each of its lines are executed. So this line overall is going to execute for V times, and these many lines overall are going to execute for 2 into E times. Why? Because 2 into E is the size of this, we have already learned. So I can say that the overall time complexity of this thing is going to be order of V plus E. Does it make sense? How many of you get the idea? Just type in yes or no. Right? Okay. So that being the reason, we will always be using adjacency list in almost all the questions, because it makes traversals more optimal as compared to the matrix representation. Okay, so I have a new question for you. The question is, let's say our graph is something like this. I can start traversal from any node and it is guaranteed I'll be able to print all the nodes for sure. But let's say now I have a graph that looks like this. If I start my traversal from this node, will I be able to print all the nodes? Yes or no? The answer is no. So let me just label the nodes. Let's say they are 0, 1, 2, 3, 4, and 5. So if you start your traversal from 0, you will only be able to print 1 and 2. If you start from here, you will only be able to print 4 and 5. The point is that if you start traversal from a node, you will only be able to print the connected component in which that node belongs. Is that correct? Yes or no? So how to handle such kind of graphs? So in order to handle such kind of graph, I don't have to change this thing at all. It will continue to be same. I'll just have to introduce few lines of change over here. And logically, how you go about it, you would say that, see, keep it in your mind that there can be many different connected components in a graph. There can be many different. So you don't know which connected component you have visited and which connected component you have not visited. You don't know this thing for sure. So what I can do is, let me make DFS call at 0. When I make DFS call at 0, what happens is it traverses this, that, and that, right? Now, you check whether 1 is already visited or not. If 1 is already visited, don't make a DFS call at 1. Similarly, check whether 2 is visited or not. If 2 is already visited, don't make a DFS call at 2. Now check whether 3 is visited or not. If 3 is not visited, make a DFS call at 3 and wait. So it will paint all these, and then check for 4, then check for 5, you will not call. So what I'm going to do is I'm going to write a simple for loop which will traverse across all the nodes. And if it sees that the current node is not visited, it will call DFS. Otherwise, it will not call DFS. As simple as that. Can I do something as brute force as this? Yes or no? Right? So that is a quite simple solution to this. So I would say that, hey, let me traverse on all the nodes from 0 to n minus 1. What should be my first line of code in this loop? Check. What do you want to check? You want to check whether the current node, which is I, has been visited or not. So if not of is vis I, it means that if ith node has not been visited, then you will be doing two things. What is the first thing? You will first mark it as visited, and then you will trigger a DFS call at I. That's it, job done. Make sense to everyone? Yes or no? Yeah. Okay, great. So what will be the time complexity now? Will it increase, decrease, or continue to be the same? Think of it. Think of it. Okay. So think of it in this manner. Guys, what will happen is, let's say you just have two different connected components in this graph. Now, let's say in this thing, the number of vertices is V1 and number of edges is E1. In this thing, the number of vertices is V2, the number of edges is E2. Okay, now look carefully. So when you start your DFS, you will first make a call at 0. When you call DFS of 0, it will take you V1 plus E1 time. Correct? Now, in this for loop, when you move to 1, you will not call. When you move to 2, you will not call. Correct? So you're not calling, so I'm not taking their contribution. They are order 1 checks, but there are no calls being made, so I can just ignore them. When you come to 3, then you will make a call. When you make a call to DFS 3, it will take you V2 plus E2 time, right? And then when you iterate for 4 and 5, you will not make the call, so just ignore them. And when you add that, what is V1 plus V2? This is total number of vertices. What is E1 plus E2? It is total number of edges. So even if you have got a disconnected graph with so many disconnected components, no need to worry. Why? Because of this check, you're not going to call DFS on all the nodes. You're just going to call on the very first member of the connected component which you catch. Is that clear? Yes or no? Okay, cool. Now let's solve a very well-known interview problem. The interview problem is that we all have been given a random graph, okay? And that graph is bidirectional, and you have to count the number of connected components. Count the number of connected components. How many of you can solve this problem? Okay. What shall be our approach? Okay, let me ask you this thing. Let's say your input graph was this, then according to the given code, how many times this line will execute? DFSI. Two times, right? Yes or no? Because you call a DFS from main function only if you encounter a new connected components. So I can have a count variable which is initially 0, and whenever I have to make this call, I can do count plus plus, and whatever is the final value of count, that will be the total number of connected components. As simple as that. Is that making sense? How many of you get that? Yeah, this is a very, very important interview question. There are several variations of this question. In fact, there are lots and lots of variations that are already there on your dashboard. Today, when you go back, make sure you watch through some of those problems. Okay, cool. For now, we will move on to the next important traversal. And so this was a depth first search traversal. And now we will plunge into breadth first search traversal. Okay. Which is BFS, breadth first search. This is also called as level by level traversal. So it is more strict in a way that it only touches nodes level by level, level by level. So let's say you have a graph that looks like this. So these zeros are the nodes that you have. Let me label them. This is 0, this is 1, this is 2, 3, 4, 5, 6, and 7. Okay. Now, I told you that, hey, in case of a graph, there is no concept of root. Because there is no concept of root, there cannot be a concept of level. So what you can do is you can randomly choose your own root. And whatever is your root, you can regard that as your level 0. So this is your root. You can say that this is your level 0 currently. Okay, so root is always at level 0. Now, what is the next level? Let us try to understand that. So the next level of this will be the nodes that are directly attached to it. So let me formalize it more. Let me formalize it a bit more. Let's say you are talking about level I. Okay. In level I, there are certain nodes, and those nodes, for example, are A, B, and C. Okay. Now, in level I plus 1, what kind of nodes will be there? So in level I plus 1, you will have direct connects of ABC, which are not yet visited. So imagine that there is a level I, and level I has ABC, 3 nodes in it. So in the next level, you will have direct connects of A, B, and C, which are still not visited. Okay. So let me ask you here, in level 0, how many nodes are there? Only one node, which is 0. So in level 1, what all should be there? Can you tell me? Just read the definition and say. In level 1, you should have children of 0, which are still not visited. Children of 0 are 1 and 2, and yes, both of them are not visited. So 1 and 2 deserve to be in this level. Okay, how about level 2? In level 2, which all nodes will be there? So when you look at it carefully, the direct connects of 1. What are the direct connects of 1? The direct connects of 1 are 0, 3, and 4. But 0 is already visited, so 0 will not be considered. However, 3 and 4 are not visited, so they will be considered. Okay, I have to do the same thing with 2. For 2 also, its direct connects are 0, which is already visited, 3, which is already visited, 6, which is not visited, so it will come over here. Okay, that is how it goes on. Can you tell me the next level, level 3, which nodes will be there? Only 5. Only and only 5 will be there, because when you take a look, for 3, its direct connects are visited. For 4, 5 is the only direct connect which is not visited. And for 6 also 5 is the only connect which is not visited. And what will be there in your level 4? In your level 4, you will just have 7 with you. So level order traversal is that which prints the nodes in this manner. If you start from a root, it will first print that root, and then the nodes in this level, and then the nodes in this level, and then that and that. Is it making sense to everyone? What are levels? Do you understand the concept of levels? Yes or no? Yeah. So now you can go ahead and get your job done very easily. But before that, I have a very simple problem to ask from you. This breadth first traversal or level order traversal is super useful for finding shortest distance. This is super useful for finding shortest distance. Okay. Here you can say that if, let's say, you are considering this path, the length of this path is 2 units. Why? Because there are 2 edges. So I'm considering one edge as 1 unit of distance. Okay. There are no long and short edges over here for now. So tell me, what is the shortest distance between 0 and 3? It is 2 units, right? If you have to go from 0 to 3, you can go like that. And what is the shortest distance between 0 and 7? Will somebody tell me that? It is 4 units. You can check that out. Okay. It so turns out that this is at level 0. This is at level 1, level 2, level 3, level 4. Can I say that shortest distance of 1 and 2 from the root is 1 unit? Check that out. Similarly, can I say that the shortest distance of 3, 4, and 6 from the root are 2 units each? Check that out. And similarly, can I say the shortest distance of 5 from the root is 3 units, and the shortest distance of 7 from the root is 4 units? Are you able to understand this thing? Yes or no? Right? So the job is done. So I can say that using level order traversal, I can very easily compute that for a given root, what is the shortest distance to all other nodes. It can very easily be computed using breadth first search traversal. And why is it happening? It is happening because I have assumed that one edge means 1 unit distance, and my edges are not weighted. Every edge has the same cost or same weight associated with it. Okay. So because the nature of this level order traversal is that first it jumps on to the nearest guys to it, and then the nearest guys to those. So it is guaranteed that it will always find me the fewest number of hops. It will always find me the fewest number of hops, or call them fewest number of edges that I need to go from root to a certain node. Okay. Okay. But if the edges are weighted, then this approach might not work. For example, let's say the distance of this root is 1 unit. The distance of this root is 1 unit. This is 1 unit. This is 1 unit. This is 1 unit. And distance of this root is 1000 unit. Okay. Now what is the shortest distance between 0 to 2? Will you say it is this 1000 unit? Yes or no? The answer is no, because there is already a shorter path than that. So this approach is going to fail if the edges have different weights. And why will it fail? I think this example explains that. Is it making sense to all? Yes or no? Right? So, whenever in an interview, your interviewer asks you for shortest distance between two nodes in a graph, the first thing you should do is you should figure out whether that graph is having different weights or same weights. Only if the weights are same, you can use BFS traversal, otherwise no. Make sense to everyone? A very, very important point to be kept in mind. Now, how to perform this traversal? So you can perform this traversal using a queue. Right? So have you guys used a queue? Learned queue yesterday? Yes or no? Yeah. Okay. So what was the last part? You'll have to tell me, like, what is the concept that you kind of missed out on? Okay, you tell me. If all the edges are of the same cost, then the shortest path from 0 to 2 is this. But if this road costs you $1,000, will you take this road or will you take this road? The answer is you will take this road. Okay. So if the edges have different weights, then you can't say that fewest number of hops will correspond to your shortest path. That's it. Okay. Cool. So now how to perform this traversal, BFS traversal. So I can do it using a queue. So what I can do is I can imagine having a queue, and in that queue, I can first push 0 because that is my route. And after that, what you have to do is you always pop from this end. And after popping from this end, you push the nodes which are directly connected to it. So you push 1 and 2. And then again, you pop from this end and you push the children of 1, which are 3 and 4, because 0 is already visited. And then again, you pop from this end and you push the children of 2, which are not visited. So in this case, it will be 6. So you basically initialize a queue with your route, and then you keep doing an operation. The operation is pop from the queue, and whatever is popped, push its children, and do this operation until unless the queue is totally empty. Does it make sense? How many of you understand the idea? Yes, no? Yeah. Okay, but in this implementation also, we need to keep track of is visited, whether a particular node is visited or not. Do we need that? We need that because, for example, if you are popping this 2, you have to know that 0 was already visited so that you don't push 0 again. However, this is a totally iterative approach. I'll quickly write a short pseudocode for whatever I have said. So you can just say, let's say there is a queue. Okay. Now you also have an is visited array of size n. Initially, nothing is visited. And now you can push 0. And because you're pushing it, you should make is visited of this thing as true. Now your actual algorithm comes, which says while the queue is not empty, you'll do certain piece of work. And what is it? You'll do queue.pop and you'll get X from here. So let's say you pop this 2 out from here. Then the next job that you need to do is you need to iterate on the adjacency list of this 2, which is X. So for every Y in the adjacency list of X, what you'll do is you'll first check whether this Y is visited or not. So if not of is visited Y, then there are 2 things that we have to do. First thing is visited of Y should be made true. And second thing is you will do queue.push of Y. That's it. Does it make sense to all? Yes or no? Okay, cool. So like those of you who would want to gain a better clarity on this, again, you need to take a look at the queues, which is there in a dashboard or which was taught to you by Bharat in a live class. And try to implement it on your own. I mean, don't ask for its solution from somebody, because now you know the logic. So you should first try your hands out on your own. Yeah, there's nothing so supernatural about it. Okay, what will be the time complexity of it? Will it continue to be order V plus E, or will it be something different? So it will continue to be the same, right? You can apply the same logic that we applied in DFS. Okay. Okay, two things that I want you to remember is, shortest path can be computed using DFS also, but that might not be optimal. And if you try to make it optimal, the logic can be quite cumbersome at times. So whenever you're talking about shortest paths in regards to a graph which is not weighted, always go for BFS. And whenever there is a question where you have to find number of connected components or anything that is related to connected components, you can go for BFS, you can go for DFS, anything of your choice. That is up to you. Okay, let us quickly solve a problem now, a very interesting problem. So this question again has been asked tons of times in interviews. So the question says that we have been given M cross N matrix. Okay. So in this matrix, the elements that you have could either be S, which is a character S, could be D, could be a star, could be 0. S means source. Source means where you want to start your journey from. You are there at your source. D is destination, where you want to go. Star means if a cell has a star, that means it is safe to travel on that cell. And 0 means that it is unsafe to travel on that cell. Okay. Now, let's say, for example, this is your matrix. Okay. And the elements it has are 0, star, 0, S. And then it has star, 0, star, star. And then 0 followed by 3 stars. And then D followed by star, star, star. It is guaranteed that there'll only be one source and one destination. And these cells, which are all stars, are safe, and these cells are unsafe. Now you are initially standing over here and you want to reach here, and you only have 4 possible moves. You can either move one unit up, left, right, or down. So you have to find me the shortest path that takes you from your source to destination. Is the question making sense? Yes or no? Okay, so if it is making sense, what will be answer for this particular input? What is the shortest path from S to D? You know what kind of moves are allowed? Up, down, left, and right. Okay, 2 of you are saying that 6. How about others? Okay, so if I have to go from S to D, maybe what I can do is I can go from here to here. This move is allowed. I can move down. Then maybe I can move down again. Then maybe I can go like that. Then maybe I can go like that. 1, 2, 3, 4, 5, and 6. So it looks like 6 is the answer. There could have been some other paths also whose length would have been 6, but I'm not interested in enumerating all those paths. I'm just interested in the smallest possible length, which is 6 over here. Does it make sense to others also that how 6 is the answer over here? Yes or no? Okay, how do I solve this question now? BFS. So two of you are saying use BFS. You know, I want to illustrate from here one most important thing to all of you. And I want you to listen very carefully to me on that. If you understand this thing, you'll be able to solve hard problems on graph. So you have to learn how to model a grid problem to a graph problem. Question will not tell you that there is a graph. Question will tell you that there is a grid. Now you have to use your senses to model that grid like a graph so that you can use graph algorithms. You see what I'm saying? Certain times you might not have a grid also. It can be a simple mathematical problem. So you have to translate that, you have to model that into a graph problem. All these things are very, very important and necessary to think about. So how do I model this thing as a graph problem? I can say that, hey, imagine as if all these nodes that are there, all these cells that are there, they are like nodes. These cells are like nodes. And then I can also imagine the edges, because if let's say there is a node over here, which is safe, then it is directly connected to this, that, and that, and that. And these edges are bidirectional. Similarly, this node, if it is directly connected to this and that, so I can imagine a graph in my head, and there will be a source node and a destination node and a set of edges, and I have to find the shortest distance, so I can get that done using BFS traversal. Is it making sense to everyone that how and why we should model this thing as a graph first? Yes or no? Yeah. So I'm not going to draw the entire graph over here, but okay, let me draw that for you better understanding. So what I'll do is I'll say, hey, this is my first node, okay? And this node is directly connected to something below it. And this is again directly connected to this. I'm going to skip the unsafe nodes because they are not fit for travel, okay? Then this thing is again directly connected to that. Then this thing again is directly connected to something below it, which is this. And both of them are again directly connected. And then this thing is directly connected to that. So this comes up. And then again, this is directly connected to that, connected below it, connected below it, and then this is connected to that. So this is one connected component of this big graph. However, there are other connected components also. So because there is a cell over here that is present here, and there is a cell here that is present over here. So this is the graphical representation of this thing. Does it make sense? Yes or no? Do you get that? Yeah. Okay, cool. Now answer me one thing. If let's say your source was in one connected component and destination was in another connected component, then what would have been the case? Would it have been possible to get a path? The answer is no, no path. So these are a few things that you have to take care of in your head. Now what you can do is you can solve this question quite easily using a BFS traversal. So you can just take a queue, and in that queue, what you are going to do is you are going to push your source first. So let's say your source is located at I, j. So you can just push here I, j, and also push something called as distance d. Okay, the distance of source from source is 0, so push 0. So what you are pushing is coordinates followed by distance. Coordinates followed by distance. And then what you will do is use your BFS. So now you don't need to have adjacency list over here, because you know for sure that if your current cell is I, j, then its neighbors will be ij minus 1, ij plus 1, I minus 1j, and I plus 1j. So if this is I, j, what you will do is you will check for this, that, and that. There are two things that you will check. First thing, whether those neighbors exist also or not. Like if this is your current node, then for this, the right neighbor does not exist. So you have to check whether the neighbor exists or not. And then you have to check whether that neighbor is already visited or not. If it happens that the neighbor exists, and that neighbor is not visited, then you will push that neighbor. So you pop it and you push its neighbor. So what is this? This is I plus 1j. You will push it and its distance will be d plus 1 because it is 1 unit away. And push the other neighbor also if it existed. So this is something that you can keep doing. You can start with a queue. In that queue, you push the coordinate and the distance, which is 0 for your source, and then pop from the queue, push its children out of the 4 children's if they are unvisited, and their distance will be d plus 1. Keep doing this thing on and on as long as you do not pop the destination itself. The moment you will pop the destination, whatever its distance will be, that will be your answer. Does it make sense? Yes or no? Yeah. Okay, cool. So in reality, what will happen is, if you're taking a look here, this is your level 0, right? And what is your level 1? This node is at your level 1. Now, these 2 nodes are at level 2. And this is at level 3. This is also at level 3. So this is how, if you simulate this algorithm, you will see that how these nodes will get pushed and how the final node will turn out with its actual correct answer. Okay. So I think this question is also there in a dashboard. So when you go back, try implementing it. It will be a good exercise and confidence booster for you. Okay. Any questions so far on whatever we have learned? We have tried to cover everything which is very basic and very important about graphs. Graph traversals, how to evaluate their complexity, connected components, shortest distance, when to apply BFS, when not to apply BFS. Okay, these are the key things that we have to understand. So munch on these thoughts a bit more. Okay, why do we store using struct? Where are we using a struct? How do we, yeah, think of it. It is again super easy. It will make your life a bit complicated. Why do you want to do that is my first question. Okay, there are other complicated questions that you should put your head on, but if you are interested, you can still do that. Just create a struct node and data will be your label, which could be 0, 1, 2, 3, label of the node. And then you can have a vector of nodes. Okay, because a single node can be connected to a lot of other nodes. So that kind of struct you can think of, but not needed, not really needed. Okay. Okay, cool. So that will be it for today. Let's meet again tomorrow. We'll start a new topic. I'll tell you about that in the class itself. But for today, spend your time with graphs. Okay, cool. So bye and have a good day.